by going to this under exercise 4, the trends, that you end up finding that there's the scaffold trend, V6 is the particular matrix trend. The fluid trend, I said just start with the gas. And the stacks, which are the stack parameters, are just the scaffold stack, and that should fill everything out here for you. I did go and then say, well, what you'd like to do is fill out and put in the true depth below mudline. Can someone tell me what that is? What that's 35335. And what's the interval velocity? 9176. Okay. And did I say 90% net to gross was sort of correct for that, right? Normally what I'll do is that here are the suggested trend values, okay, for that depth and that LFIV. Many times I like to just check what's going on here, and I just do that by just saying paste special in terms of that whole row to get the same values. I also go down here for the fluid to do this to a copy and then edit sort of paste special values. And also end up doing the same for the stack parameters. And just do an edit paste special values. And then I'll just go over and take a look at the outputs to sort of see, you know, here's about the intercept is about 13% reflectivity. Maybe if I went back to 0% saturation, that goes from 2% to the, 13%, just to get an idea of that. The near stack and far stack are about 15%. You can see that the stack angles are about 17 and 23 degrees, as they should be. And even to get some idea that, oh, this beta is about 15% on this rock, then I'm looking at the porosity is about 29%, okay? And again, just to sort of get a particular idea. And the next part that I have you go through is to say, and this stuff is actually set so that there really is no noise on the data. And I'll just sort of told you to sort of go and do the scatter diagrams and take a look at them. It took a while to think. Okay. Then you take a look at the graphic output. Here's that LM plot like you'd probably be used to from the Hess viewpoint. And then you also see the sort of this is sort of the background normal direction, which we really haven't defined yet. What the near and the far stack humps look like. They don't look very good because they're only 100 points. How things look like on the near and far stack space, okay? And what I ended up asking you to do was to say, okay, we go and see that the brine reflector here is about 7%, and that we need to go and set a noise level. And normally I go and say that the noise level ends up being about 1/3 of the size of the brine reflector. And so that I'll go and say then, therefore, the near stack ends up being, let's say, about 2% for the near, maybe a little bit more than that for the far, which is sort of a 10 dB sort of signal to noise ratio. And then end up going sort of the 0.06 in the parallel direction. I know it's about 1/3 of that in the perpendicular direction. And then go, and I'll say, go and now let's do it again, but putting this particular noise level on it. And you'll see that there ends up being, these end up being a little bit more scattered, and especially in the near far space. And now we can start asking about what some of these optimum sort of directions are for the separation. And that's where I've asked you to sort of press some of these red buttons, or to say, okay, now given that, sort of what is the optimum slope of the background normal here, okay? And well, the optimum slope ends up being sort of minus 4.1, So I can go back here and say that the slope of that ends up being that minus 4.1. And you end up seeing over here on the graphic that now this particular sort of lithology direction ends up being defined here. And you'll see that it tends to be aligned along the direction associated with these. And the noise direction, or the direction that noise is being added on with, should be, in this case, this minus sort of 5.9 direction, which is sort of the estimated sort of noise slope. And this is actually a fairly complicated formula that comes from sort of a prediction, and will be sort of dependent upon the noise level that you end up putting on it in general. And so those are the sort of the first steps I've sort of asked you to go through, to sort of go and sort of find out what these optimum directions are. And I also ended up asking you to pick up what the optimum sort of separation direction is in the near far. But after you play with this a little bit more, I'll talk a little bit more about these noise slopes and these particular optimum slopes after you sort of get a little bit more used to it, okay? But again, just sort of go through the steps, and I sort of give you a little bit of a preview now of the way to do a couple of the first steps in the process. Okay?
Exercise 4, and what are we trying to do in exercise 4, okay? And the goal of exercise 4 is to get hump plots and to understand what the average reflectivity is of a shale on shale reflector, a shale on brine sand reflector, a shale on oil sand, and a shale on gas sand reflector. Not only the most likely value, but also a range of values, okay? And also, right at the end, I think there's a particular question asked earlier, in the course about what makes a difference, or what's causing things to be, as wide as what they are. And you'll see that in as step 5 in exercise 4, I tell you to go and take a look at the particular sensitivity chart, okay? And right at the end, I'll actually go through that and show that to you, okay? And also, the early parts of this exercise, it sort of seems there are some particular mechanical steps I talked to you about in terms of setting the noise levels, okay? But really what this was about was fairly simple, is that we have to add on and see whether or not the width is being controlled by the amount of seismic noise that we have, or is it the quality of the seismic noise and your ability to discriminate that's causing that. And the prescription that I showed by setting it to 1/3 the amplitude is just saying that the average noise level ends up being about 10 dB, okay, which is a good signal to noise level. We'll talk a bit later on of more quantitative ways of determining the noise level, but many times we just do this to say, if I have an average noise, or sort of a good noise, floor, a low amount of noise, what is the effect that I expect? If you go and say that I have a lot of noise on the data, and it's about the bips and bobbles which don't sort of tie, or sort of equivalent to the size of the brine reflector, then you should go and set the particular noise level to the size of the brine reflector. So until you start looking at well ties or your impressions of what the particular noise level is on the data after taking a look at it, that really should inform the setting of the noise level, which is what was in the early part, okay? Then there are some other things with respect to these slopes that you end up setting, and that when I talk about what the best directions were when I had those 3 shotgun blasts out there, well, you can sort of look and tell what they are, but these spreadsheets have the ability of doing some statistical analysis to be able to tell you what those directions are, and that was what was behind those particular questions, okay? And again, to orient you in terms of what we're doing, that if you take a look at your flow diagram here, and let me go up to the front of the class, that we're working right now in rock physics, and that we've taken in the results of the LFP analysis. And again, what we're trying to find here are what these particular humps are, okay? Or the average amplitude response and also the range in the amplitude response, okay? I'm going to give you about another 10 minutes to work on this, and then I'll go and walk through the sensitivity analysis and also talk a little bit about where the particular humps come from and what they are for this particular case. Okay? Review something about the results here. And now let me just go and talk a little bit about what's going on here. Over here on the left-hand side is this LM plot, where the intercept is along this direction, the slope is along this direction. As Guy Duncan pointed out, that the class 1, class 2, class 3, class 4 is really in reference to this particular picture. Historically, we started with this type of analysis. Shell published their results, and then we ended up modifying it and adding on the near far part on the right-hand side. Here you can see that the particular noise direction ends up being along here. And what's sort of called the background normal rotation comes about from the fact that naturally these clusters like to be aligned along this direction. But as you add more and more noise on it, because it has a correlated effect, it rotates this optimum direction all up to here, and that's normally called the background normal rotation. As Dave talked about the other day, the background line is aligned along the shale reflector, and the normal to it ends up being the perpendicular direction. And also what you end up seeing here is that we show this lithology direction, and that ends up being what was calculated when you pressed this red button that I asked you to. And you ended up putting that in, and that defines this red line. And that is the lithology, or the background direction. And the background normal to it is in this direction, and these clusters collapsed along the background normal is what's sort of shown here as this fluid factor, or again, that's sort of the background normal, or I guess the perp as direction, as Jacques Levitt at Hess has called it in the past. We also show the near and the far reflection strengths. We also have the numbers associated with the mean and the standard deviation of each of these. And Rick, I think, had a very good observation, was these pictures look a lot alike. These pictures looking alike means, as I talked about before, that there isn't a lot of value of having two stacks over one stack. You can see that it gets a little bit brighter on the far, but everything gets brighter by about the same amount. And it's a modest amount if you looked at it. Now, if we go over here to the near and the far plots, there ended up being a few more numbers in terms of the separation here. And one is, what is the best direction that will separate all three clusters sort of at the same time? Then there's also a particular direction that's associated with separating the shale from the brine and the brine from the hydrocarbon. And those you can see are a bit different here. And if you also took a look at those particular directions define this red line, and that the coordinate ends up being the perpendicular to it, and you can actually choose these different, sort of directions. But then you'll ask, okay, at that perpendicular direction, what does that mean in terms of combination of the near and far? Well, here are the multipliers. Here's the cosine theta and the sine theta, the cosine theta and the sine theta. And you can see that in order to separate the shale from the brine, or the black from the blue cluster, it likes the far stack. And in order to separate the green from the blue cluster, it ends up preferring the near stack as the larger multiplier here, okay? And again, it's done that by just a particular statistical cluster analysis. And also, that if you want to know what the ellipses are that actually define the shale cloud, the brine cloud, and the hydrocarbon cloud, if you click here, it goes behind the scenes in MATLAB and will fit these ellipses to it. So it's a version of the plot that you see here, but it's been calculated in MATLAB. And it also tells you the center of those ellipses, the size of the major and minor axes, and the orientation of the major axes, okay? And you'll see that when we get into the AVO analysis, that you'll need to know the location of the shotgun blasts, and these are the numbers that define the location of the shotgun blasts. And then the final thing that I asked you to do here is to go and form up the response summary. Let me go back up. Okay, here's the response summary. And all I did was to go into the rock physics. I went over to the particular near stack, collected the mean and the standard deviations for these three cases, and then reloaded the particular fluid trend for the oil case, and reran things in order to get the oil, and then copied that extra fourth column. And what you end up then getting is the response and sort of the standard deviation for these four cases. And you can see that the gas is well separated from the oil. There's a particular amount of overlap of brine and oil, and also a particular overlap of shale and brine, but not much overlap between the shale and the oil. And it's this little seriatim is what's going to be needed for the next analysis, okay, in terms of interpreting the amplitudes and doing our Bayesian update later today. And then the last thing I asked people to take a look at was to go into the rock physics spreadsheet, go underneath here, underneath the particular sensitivity charts, to go and pick that particular sensitivity chart and look at that sensitivity chart, okay? And what this ends up saying here is that the VP-VS sand trend ends up being the thing that contributes to the uncertainty or the width of the peak associated with the far reflection coefficient. Next is the VP depth or the compaction trend for the sand. Then next underneath that is in sand fraction, okay? Can anyone sort of tell me, sort of what does this tell you? If I wanted to reduce this uncertainty, what type of information should I acquire? Any suggestions? A shear log, okay?
And anyone that knows that subsequent to this in this area, we had recognized we were really using sort of regional VP-VS relationships because we didn't have sufficient information. If you remember back when we formed the trends, and I asked you to make that mixture. And so we've made sure in this area we've gone and spent the money to acquire good shear logs. And so that, again, it's a value of information-based thing, that we didn't say that we wanted to go and acquire more density or better density logs, or so that you can point to this and say, this is the reason why we want to acquire that log, okay? Because it's going to allow us to high grade and be able to discriminate things better. Below that, you see it's a VP depth trend. And so that's why we've always paid a lot of attention here to trying to understand exactly what type of rock we're dealing with in order to be able to go and understand what the compaction state of these rocks should be. Down here on sand fraction, that's really around geologic variation and understanding how much of a change you can expect in net to gross as you move around. And so this ends up being predominantly a geology question. But if this is just what you expect and it's sort of an irreducible sort of geologic uncertainty, and you've gotten these down to below here in sand fraction, that ends up being a particular statement that this is what you've done as much work as you can in order to reduce the uncertainty, and that it would not be worth, let's say in that case, going and improving the signal to noise of the seismic data any better than what it is, because the uncertainty is being dominated by a geologic uncertainty in sand fraction, okay? So it wouldn't be worth going to large amounts of effort in order to improve your seismic signal to noise level, which could be quite expensive, especially if it means reacquiring the data. And so that you wouldn't go and wouldn't be able to justify, at least from this perspective, an improvement in the quality of the seismic data, okay? And the reason why I'm bringing this up, and this is, I think, going to be the particular questions that have been asked about us in the mining industry, is what boreholes should you add to things? Or how should I drill another borehole? Should I acquire some more seismic data? And that going in these type of sensitivity analyses in terms of the things that you're trying to estimate or try to get below a particular threshold end up informing and can either help you justify particular amounts of data acquisition, or it can tell you when you should stop acquiring data, that things are good enough in terms of what the uncertainty is. Okay? That's the reason why I've taken a little bit of time here with respect to sensitivity analysis, since it actually is, I think, a very important thing that can inform decisions going forward. Okay? Again, if you want to go and talk to me and about where you ended up getting stuck, I mean, I think I saw people were really working their way along here, and probably amongst the courses I've taught, I mean, I do have to say that from what I've seen, that people have really in this course gotten stuck the least, and have really been zooming through this stuff like a hot knife through butter. And I really, commend everybody in the course, because I do recognize too that we have some people that are quite familiar with things, but there's also another cadre of people who are very early on the learning curve, and that they're coming along really quite well. So I think you all should feel good about your progress on these exercises. Okay, I'm going to go and flip over to the presentation now, and that